Hello everybody, this is the video clip for Calculus Business 2, and this one is the first chapter, and the video clip is the first video for the first chapter. For this chapter, we are going to talk about the so-called matrix, okay, and we are going to learn how matrix operate. So this chapter is called matrix algebra, all right? So let us start. Matrix is the mathematical object, okay? It is the arrangement of object, and usually those objects should be the numbers, okay, like this. The arrangement will be in terms of a row and a column, okay? In terms of a row and a column, we usually start by a row. So this one from the top, it is the first row, and then the second row, the third row, and the fourth row. And then this one, the column from the left, the first column, the second column, and the third column, okay? And the number of row and the number of column determine the order or the size of the matrix. For example, this one has 4 rows and 3 columns, so it means that this matrix is of the size 4 by 3. So we call 4 by 3. We don't say 12, okay? We call it 4 by 3, so that we know that here, okay, the first one represent the row, the number of row, and the second one represent a number of column, okay? And each and every position, okay, in the matrix got their own name. For example, this one is the element on the first row and on the first row and the first column, so we call it as A11, okay? So this one again, the first subscript here refer to a row, and the second subscript there refer to a column, so we know which one that we're talking about, okay? So it means that your A11, it is the 1, A12, which is the first row, the second column, it is -2, you see here, and then A13, okay, the first row, the third column, it is 4, and then A21, it is a 0, you see, and etc. up to A43, it is y plus z square, you see. Okay, so this is the matrix, all right. And in general, okay, if we have this is the first row, the second row, up to what? Where is the row? The row is the first subscript, right? So you got m row, and then here the first column, the second column, up to the what? Here determine the column, right? The nth column. So this one contain m rows, n columns. So here the size of the matrix is m by n, and usually we are going to abbreviate it. Instead of, you know, expand it like this, we are going to contract it into aij, okay, aij, and then m by n, okay, m by n, all right. And of course, I mean, don't forget that if we have only one row, one column, okay, which is the, I mean, the matrix of the single element, okay, this one is a matrix, okay, but this one, I mean, if you just write down the A, it is the real number, right? They are different, they are not the same. So it means that the matrix 8 and 8, they are really not the same, okay? They are different object, right? There are spatial matrices, okay? For example, the first one, if you have, I mean, all the elements are 0, we call a 0 matrix, okay, a 0 matrix. So it means that all of the aij equals to 0, and it can be of any size or of any order. For example, this one got 2 rows and 3 columns. So you see the first row, the second row, the first column, the second column, the third column, they are all 0. This one as well, This one is a zero matrix of size 1 by 2, so you got only one row and two columns, okay, but both of them, I mean, they are zero. Another one, it is a square matrix, okay. A square matrix, it means that your row and the column, okay, are the same. For example, this one, it is 1 by 1 matrix, this is 2 by 2 matrix, and this one is 3 by 3 matrix, okay. So this is pretty straightforward, right? And then the as we got the square, you have the diagonal, okay. Actually you have two diagonal, right? But the one that we usually concentrate on, it is the one from your upper left to the lower right here. This one is so-called a main diagonal. For example, this one, I mean, even though you got only one element, this is a main diagonal. Here, this is the main diagonal for the second matrix, and there is the main diagonal for the third matrix, okay. All right. Another one is so-called a diagonal matrix, okay. For the diagonal matrix, it means that you got the non-zero, I mean, element. Actually, maybe it's not a non-zero, but all the element that you concentrate is on the main diagonal, but then the rest, you see, the rest, they are all zero. This one is called the triangle, the upper triangle. This one is called a lower triangle. The upper and the lower triangle elements, they are all zero, okay. The upper here and the lower triangular, they are all zero, okay. So what does this mean? It means that the zero matrix, okay, it also the zero matrix with the same row and the same column, they are also diagonal matrix, okay. Because actually we don't really care what happened on the diagonal, we just care the one outside the diagonal, okay. It must be zero, it must be all zero, and your matrix must be, you know, square, okay, square. All right. Another one is so-called a triangular matrix, okay. A triangular, for example, this one, the upper triangular, it means that all the element, okay, all the element including the main diagonal, okay. This is the element that we concentrate on. So it's look like these elements, okay, accumulate up there. The one outside the main diagonal and the upper part of the main diagonal, they are all zero, okay. They are all zero. So it means that as your I greater than j, your aij are all zero, okay. This one is so-called upper triangular. So the upper means the one that you concentrate on here, and the lower triangular is the same thing, the one that you concentrate on accumulate, okay, for on the lower part of your diagonal and also on the main diagonal. But then the one outside this lower part, they are all zero, okay. They are all zero. This one, the so-called lower triangular, okay. Of course, I mean, all the triangular matrix, again, it is the square matrix first, okay. Another one that you may encounter, it is a row matrix, okay. The row matrix, it means that you have only like a single row, okay, with several columns, okay, only a single row. For example, this one, you got one row and 3 columns. This one, you got one row and 4 columns, okay. And another one is a column matrix. A column matrix, it is a single column with several rows. For example, this one, you got 3 rows and 1 column, 4 rows and 1 column, just like that, okay. So as you know the what is the matrix, then you are going to, you know, compare, okay, the matrix. By compare, okay, the one that you can do is only equal, okay, whether two matrices are equal or not, okay. So for example, if you given the matrix A and the matrix B, okay, your two matrices are going to be equal, of course, if they should have the same form, right? By form, it means that they should have the same order, okay, the same number of rows, the same number of columns, okay. And of course, I mean, if they are going to be equal, then each and every position must be the same, is it? So they are going to be equal, I mean, position wise, okay. For example, of course, I mean, this one, it is not equal because here you got one row and two column, but this one you got two row and one column, so they are of course not the same, okay. This one, even though the number of row and the number of column are the same, the first position they are okay. I mean, this is A11, A12, they are the same, A21, they are the same. However, this one, A22, they are not the same, okay. This one is a rational number, this one is a rational number, okay. They are not the same, so it means that these two matrices, they are not really the same, okay. So this one, if we are given that these two matrices are equal, okay, of course, I mean, the form, they are okay because they got two rows and two columns, okay. They got, you know, A12 are the same, A22 are the same already. So if they are going to be the same, it means that this one must be equal, so A plus B must be 5, okay. On the same token, this one must be equal because they got the same position, right? So the 2A must be 8. So you can solve the second one first to get your A as 4, and as you get your A is 4, then you go back to this one, your B is 1, okay. Very simple, right? So it means that these two matrices are going to be the same if your A is 4, your B is 1, okay. Your B is 1. However, let's take a look. I mean, they got the same size, right? And these two elements are already the same. However, if they are going to be equal, okay, if they are going to be equal, then A plus B must be 5, and the 2A and the 2B must be 8 at the same time, right? This is N. However, from the second equation, you got A and B equals to 4, okay. Can it be, I mean, the same pair of number, can it added together and one of them equals to 5 and then the other equals to 4? Cannot be, right? This is a contradiction, okay. So it means that I mean, no matter you choose the A and the B, these two matrices cannot be equal. It cannot be equal, right? Another operation, okay, of a matrix, okay, which you are going to encounter is called the transpose of the matrix. Pose, it means position, okay. Trans, it means change. So this one, you change a position of your matrix, okay. And by changing it just simply change the row into a column, okay, and a column into a row. You know what I'm saying? So this one, the whole row becomes a column of the A transpose, and you are going to use the superscript capital T to indicate that you do a transpose, okay. And this one, your second column here, okay, becomes the second row here becomes a second column of your A transpose, okay. So it means that if this one, it is like 2 by 3 matrix, the transpose becomes a 3 by 2 matrix, okay. So if your A is a M by N matrix, then your A transpose, it is immediately N by M matrix. So if it is a square matrix, then the size doesn't change, but of course the position changed. Okay, for example, this is the row, it becomes a column of the B transpose. Okay, and this is the column, it becomes a row of this B transpose. Okay, and of course if you do transpose and then another transpose, okay, I mean followed by another transpose, it will go back to your A itself, okay, at the original. Okay, because you do change one time, then you change another time, then of course it go back to the same A. Okay, if you want to do the addition, of course, I mean you need to have the same position to add, right? You need to have the same position to be added. Okay, so if you got a different sizes of matrix, then you may not be able to add. Okay, so at the first requirement is that your A and your B to be added must be the same size, m by n, okay, m by n, and then to do the addition, you just do the position wise addition. Okay, so it means that the same position just added, just like that. Okay, the same position added. All right, this is very straightforward. For example, if you need to do this one, this is a 2 by 2, this one is also a 2 by 2, and you need to add it. So it means that this one, it is a 2 and 1. So at first, negative 2 and 1 becomes the first A11, which is in the first row and the first column, and then a second position, the first row and the second column, it is 5 and 9. This one is 7 and 4. This is 0 and 4. So after you really do the addition, the first one becomes a negative 1, a 14, 11, and a 4. Okay, and this one as well, you got a 2 by 1 and a 2 by 1 matrices. Okay, so as you add them up, so it means that this first row just added, so you got 1 plus x squared, and also the second row added, so you have actually what, x plus negative 4x, and it is become negative 3x. Okay, so if you have the different size, okay, so this one is 4 by 1, 2 by 1, this one is 2 by 2, so the addition cannot be defined. Okay, cannot be defined because you see, I mean this position can be added, but this position has no one to add, so you cannot define the addition for this kind of matrix. Okay, of course, I mean the matrix got the properties, okay, for addition. For example, because I mean if they have the same order, okay, they must be the same order first, so that they can do the added. Okay, the first one, because after you have the same order, by adding it means that you just add numbers at the same position, right? So by add number, you have a so-called commutative, so you can do the first one followed by the second, or the second one followed by the first, it doesn't matter. So this one is called a commutative property. Okay, so A plus B equals to B plus A. And also the associative, if you got 3 matrices added, you can do the A and the B first and followed by the A, or you can do the A and the B first and followed by the C. They got the same thing, or sometimes you can just ignore the parentheses and using this A plus B plus C. Okay, it doesn't matter. And you got the identity, of course, I mean because you have the if A is a real number, A plus 0 is the A, and it is the same as 0 plus A. So it means that if this one you got a 0 matrices matrix, okay, and then your A added by 0, it is the same as the 0 matrix plus the A, and you get back the A itself. So this one is so-called the identity. Okay. Another kind of operation, it is the scalar multiplication. The word scalar, it means that you talking about a number, so, okay, and this number, it is actually a real number, not matrix, okay, not a matrix. All right, so if you have a matrix A with any size, okay, it can be of any size, and your K is just a real number, okay, and this one, the real number in this chapter, usually is called scalar. Then the multiplication of the K with a matrix A, it is the position, I mean, it is a position wise, can we say it like that? It is the distribution of your K into each and every element of a matrix A. Okay, so it means that each and every element of your matrix A will be multiplied by that constant K. Okay, by that constant K. For example, if you are going to multiply the 2 with this matrix, so it means that your 2 is distributed to each and every element of your matrix. Okay, so this is the result, because 2 and negative 7, it is negative 14, 2 and 4, it is 8, 2 and 2.5, it is 5, and 2 and 3, it is 6. Okay, or this one, it means that your A multiplied with x, so you got ax, and your A also multiplied with this polynomial, so you got 3a minus 2ax. But of course, if the scalar is 0, then upon multiplication, each and every element becomes 0 like this. So it means that you obtain a 0 matrix. Okay, obtain a 0 matrix. There will be a property of a scalar multiplication. So if you have your A and B added and you got a scalar K multiplied outside, so it is the same as you just multiplied your K to each and every matrix and then you do the addition. If you got 2 scalar added and then multiplied by a matrix A, you can just distribute the A into each of the K to got K1A and the K2A and then do the addition. If you have K1 and the K2 multiply to the matrix A, you can do K2 and A first, or you can do K1 and K2 as a scalar first and multiply that one scalar to the A. Of course, as we did in example, if you have a scalar 0 multiplied by a matrix A, you obtain a matrix 0. And can you notice that if we are talking about scalar, this one is a normal case number, but this one will be a boldface. Okay, a boldface means a matrix. Okay, in this lecture note, if you got any scalar multiplied by a matrix 0, you got, of course, a 0 matrix. Okay, just like that. If you want to do a subtraction, it's really straightforward. Okay, the negative A, okay, the negative A, it's simply a negative 1 multiplied by A. So it means that each and every element in the matrix A will be multiplied by negative 1, or it will just change the sign, right, of each and every element in A. And your A minus B, okay, your A minus B, it is actually your A plus with a negative 1b. Okay, so this is pretty much the same as your numbers, okay, as we work with a real number. Okay, so for example, if you're talking about a negative 1 and a matrix A, B, C, D like this, so it means that each and every element, it is multiplied by negative 1. So you have negative A, negative B, negative C, and negative D. And if you're talking about these two matrices subtraction, then it means that actually it just refers to the same position, subtract each other, just like that, right? Just do the same position subtraction. So this one, the 1 and the 1 cancel, so you got 2x. This one you cannot further simplification. This one you got a 3, and this one you do a x minus 6, you see. So that's pretty straightforward for addition, subtraction, and multiply by the scalar. Okay. However, the thing that is not that natural, it is the matrix multiplication. Okay, matrix multiplication. If you got your A and you got your B, okay, it must be of something that not really natural. The first one, your A must be of the size m by n. Your B must be of the size n by p. Okay, you see, your A must have n columns here, and then your B must have n rows. So the column of your A must be the same as the row of your B. Okay, but then your result, okay, the resultant of your multiplication, it is of the m row and p columns. Okay, it is this size, m rows and p columns. Okay, and how we do that? We are going to do the whole row multiplied by the whole column. How you multiply? I mean, that's why we need to have the same number of column and a number of row. Okay, so we are going to do the 3 multiplied by 4, okay, the 5 multiplied by 1, and the 2 multiplied by 3. And after you got a multiplication, you are going to do the addition of these 3 multiplied. Okay, so the first one, 3 and 4, you got 12. The second one, 5 and 1, you got 5. The third one, 2 and 3, you got 6. And then after you add them up, you got 11 and add by 12, so you have 23. Okay, and this one, because it is come from the first row and the first column, you are going to write it down for your first row and the first column as a result. Okay, so if you move, okay, this one still the first row, and you move to the second column, so the result will be here. Okay, the first row and the second column. Okay, what is this result? It is a 3 multiplied by 2, 5 multiplied by 3, 2 multiplied by 2, and then you add them up. So you see, 3 and 2 is 6, 5 and 3 it is 15, 2 and 2 it is 4. So you got 25 out of it. All right, so you move to the next position. Okay, you keep the first row, but then you go to the third column. So you are going to obtain this one, which is C13. Okay, the first row, the third column. So here the 3 multiplied by 1, 5 and 5, 2 and 6. Okay, so here 3 and 1, 5 and 5, 2 and 6. So there you have 3 and 25, which is 28 and 12. So you got 40. If you move further, because I mean, can you fix the first row and the fourth column? You don't have it, right? So you are going to do the second row. Okay, now the second row and the first column, whereas the second row and the first column is right there, right? C21. Okay, so it is 1 and 4, 2 and 1, 4 and 3. See, 1 and 4, 2 and 1, 4 and 3. So you have 18 out of it. You move to the second column here, 1 and 2, 2 and 3, 2 and 4. So 1 and 2, and this is the second column, second row, sorry, and the second column. So you are going to got this one, which is C22, second row and the second column. So you have 2, you have 6, so it is 8, and then another 8, so you have 16, right? and then you move to the last one, okay, which is this one, the second row and the third column, okay, right here. So you have 1 and 1, which is 1, 2 and 5, it is 10, so you have 11, and then 4 and 6, it is 24, so you got 11 plus 24, which is 35 right here at C3, C23, second, you see, second row, third column, so you have C23. So this is how you do a matrix multiplication. Okay, it is a little bit complicated, and the order of multiplication, of course, important. Okay, in general, the A and the B is not equals to the B multiplied by A. Okay, I mean, of course, the order can be one of the thing that indicate. Okay, if your A is of order 2 by 3 and your B is of order 3 by 4, I mean, you can do the A times B, right? Because the number of column of A, it is the same as the number of rows of B, and your A times B becomes the size of 2 by 4. Okay, however, can you find the B times A? So your B it is 3 by 4, your A it is 2 by 3. The number of row of your B is not the same, the number of column of your B is not the same as the number of row of your A. So it means that your B times A is not defined at the first place. Okay, so I mean, this is one of the example. Okay, another example is that if your A is of order 2 by 3 and your B is of order 3 by 2, okay, so you can see that a number of column of A is the same as the number of row of B. Okay, so the A times B is defined, and your A times B, it is the matrix of order 2 by 2. Okay, right here. Okay, it is a square matrix. And if you talking about the B, okay, if you do the B first, which is a 3 by 2 matrix, together with your A, which is a 2 by 3 matrix, so your column of the B and the row of the B of the A, they are the same. So it means that your B times A can be defined. Okay, you can find the B times A. However, the size of your B times A becomes a 3 by 3 matrix. Okay, so I mean, your A times B has this order. Okay, is only like 4 elements in there, but your B times A has this order, got a 3 row and a 3 columns, so they got like 9 elements in there. Of course, your A times B and your B times A are not the same. Okay, so even though if I mean you got a square matrix like this, a 2 by 2 and a 2 by 2, okay, which is, I mean, either way you do a commute between the A times B or the B times A, you still got the same order. Okay, however, I mean, in general, if you really perform a multiplication, for example, this one, okay, you are going to have 1 multiplied by 2 and the 2 multiplied by 1 added together. So the first row and the first column of your, so let's say this is A, this is B, this is A times B. The first row and the first column, the A11 of your A times B, it is 4, right? A 2 plus 2, so you got 4. However, if you do a B times the A, this is B times A, okay, you do the row multiplied by a column. So this one, you got a corresponding multiplication is 2, and this one a corresponding multiplication is 8. Together you got a 10. So you can see immediately that the first position, I mean, at the first row and the first column, they are different already. You see, this one is 4, this one is 10. So it means that, I mean, of course they are not the same, because at the same position they contain a different element. Okay, and you can figure the rest of the element by yourself. Are we good? Okay, whether, I mean, how are we going to get a 14, how are we going to get a 16? Okay, so you do row multiply a column. For example, this one is 1 and 4, so you have 4, and this one is 2 and 5, so you got 10, so together you got 14, and this one you got this first row, second column, okay, to obtain the 16, which is what 2 and 2 is 4, and 4 and 3 is 12, so 12 and 4 together is 16, okay, just like that. However, can we have some special pair of A and B that your A times B and your B times A equal? So this one is only a special case, okay? So in general, they are not the same. This one is only a rare case that they are the same. Of course, one of the cases is that if your A is a zero matrix and your B, it can be any matrix that you can find a multiplication of A and B together with the B and the A, okay? So if, each and every element are 0, upon multiplication you got, of course, a 0, right, at the first place, for the first row and the first column, and the first row and the second column is also a 0, and of course second row and the first column you got a 0 as well, and then this one, the second row and the second column you got also 0, okay? So this is one of them that you of course, A and B or B and A multiply, they are the same because one of them are all 0 matrix, okay? And the result will be the 0 matrix itself, okay? If A times B and B times A are meaningful, okay? Another example is that if your A is this one and your B can be any square matrix like this, okay? This is a 2 by 2, this is also a 2 by 2, and then you do a multiplication, okay? So the row multiplied by a column, so only the first one survive, okay? The second one multiply with 0, so you have a 0, right? So you got the A. And then the first row multiplied by the second column also, only the first one on the second column survive, so you have a B, okay? And then if you do the second row with the first column, then the 0 will multiply with the first one, but 1 will multiply with your second element on your first column, so you have a C right here. And then this one, the 0 will multiply to B, and also the 1 will multiply this D, which is D itself here. The same thing happened here if your A times B, if you got a B times A, okay, if you commute it, okay, this one, A multiply with 1, B multiply with 0, so you got A. The second one, your A multiply with 0, your B multiply with 1, so you have a B right here. And this one for your second row and the first column, so your C multiply with 1, so you have a C, and then your D will go with 0, so it's gone. And the last one, your D multiply with 1, so you have a D, okay, and your C multiply with 0 over there, so you have nothing, okay? So this is the the special matrix multiply with the 2 by 2 matrix. You got the same thing, okay? You got the same thing back. This one sometimes is called the identity, okay? This one right here, sometimes it's called identity matrix, okay? And usually we refer it as IN, a capital I subscript N, okay? So this one is a square matrix N by N, and then the element along the main diagonal, they are all 1, and then the rest outside the diagonal, it is 0, okay? So for example, if you're talking about I3, so it means that you got 1 0 0, 0 1 0, and 0 0 1, okay? And this one, of course, it is your what, I2, okay? And then from this example, you know that if your IN multiply with A, of course your A must be the square matrix n by n, it will equals to A, and it is the same as your A multiplied with the identity. So your identity in the matrix here play the same role as 1 in your real number. Okay, play the same role as 1 in your real number. Okay, this is one of the example. And another example, this is very special case. Okay, is that, hey, there will be some pair that your A times B and B times A, they are the same. So let's look at this one. Okay, here the first row and the first column. Okay, so you got a 1 and 9, which is 9, and 4 and -2, which is -8. So you got 9 minus -8, which is 1 here. Okay, so you have this one. How about this? Okay, the first row and the first column. So you have 9 and 1, which is 9, -4 and 2, which is -8. So I have 9 minus 8, which is 1 as well. So the first row, the first column here, and the first row, first column there obtain the same result over here. Okay, so you got 1. Okay, so how about this one? If you look at this first row, second column, so you got 1 and -4, which is -4, and this one 4 and 12, which is 48. So 48 minus 4, it is 44 right here. You see the second row, the first row, second column. So look at the same place, the first row, second column. So you have 9 and 4, which is 36, and then -4 and -2, which is 8. So 36 plus 8, you got also 44. Okay, this is your first row, second column. Okay, look at this one, second row, first column. So you have 2 and 9, which is 18, and then -2 and -2, which is 4. So 18 plus 4, it is 22. You see, second row, first column. So look at this one, second row, first column. So you have -2 and 24. You see 24 here. 24 minus 2, so you have 22, of course. Okay, look at the last place. Okay, the last place here, you have the second row, second column. So you have -8 and -24. Okay, -24 and -8 together, you got -32. Okay, as a result, here is your second row, second column. Look at this one, second row, second column. So you have -8 and -24 as well. So -8 together with -24, so you have -32 as a result. Okay, so this one, your A times B or your B times A, they got the same answer. Okay, this is a very special case. Okay, all right. So let's look at a property of the matrix multiplication. Okay, so as we told you that normally AB and BA, they're not the same. Okay, normally they're not the same, only a special case that they'll be the same. So this one is not a property. Okay, so the first property is called the associative. So it means that if you got 3 matrices, and if you do multiplication, okay, you can do the B and the C first, and then followed by the A, or your A and the B first, and then followed by the C. Okay, but you cannot switch the order. So sometimes you can ignore the parentheses and just write down ABC, just like that. Another one is distributive property, which is the left distributive here. Okay, this is from the left. So your A times B and your A times C can distribute like that. And this one, it is your right distributive, which is a distribute from the right. So here is A times C and B times C, and you cannot switch the place. You cannot switch the order. So this one, your C is on the right, so it must be on the right of your A, and it must be on the right of your B. If you got a scalar, this one is just number, or in this chapter we call scalar. multiply with the multiplication of A and B. Then you can do A multiply B first, followed by the multiplication of K, or you can do KA first and then multiply with B, or you can, because this K is a scalar, so your K can multiply with B first and then after that multiply with your matrix A. But again, you cannot switch the order. So if your A is on your left of the B, it has to be on the left, okay, all the time. And of course, if you multiply with a zero matrix, so you obtain a zero back, okay, just like that. If your A times 0 is meaningful, or your 0 times A is meaningful, okay. Another one is that if you do a transpose, okay, you got this first property is already you already know that if you switch the row and the column and then you do switch again, and it will go back to the same thing, okay. However, this is a very special case for a transpose, is that if you do A plus B transpose, it will be the same as you do the A transpose first and then followed by the B transpose, the minus as well, okay. You can do a distribution of the transpose. If you got your scalar K, because the scalar is not any matrix, they has no row or column, so you can just pull out the scalar and then find the transpose only for your matrix A. Number 4, it is very important, is that if you do A times B and then transpose outside, it will be the same as you do a B transpose first multiplied by A transpose, okay. So you do have to switch, you see, you do have to switch the order of your A and your B, okay. This is very important. And as we told you about the identity matrix, okay, so this one is the n by n matrix, and your main diagonal, they are all ones, and then the rest outside the diagonal, they'll be all 0, okay. So this one is I2, this one is I3, okay. And the property of the identity matrix is that if your A is the n by n matrix as well, and this is a IN, then your matrix A multiplied with the identity, or the identity multiplied with your A, will go back to the A itself. We get? This is the example that we already did before, right? When your identity multiplied with A. And this one is for the 3 by 3 matrix. If you have this one multiplied by this matrix, then it is the row multiplied by a column, but the one that survives will be the only first position, you see, because the rest will multiply with 0. So you got 2, of course. If you sweep to the next column, the only first element again survives, so you got 3. If you sweep further to the third column, the only thing that survives will be a negative 1, okay. So if you go further, sweep for the row, okay, and then now the second row and the first column, the one that survives will be the middle one, because the first and the third one multiply with 0, so it will be all gone, so you have 5. And the middle one of the second row also survive with your second row, and the middle one of your third column will survive with your second row, like that, okay. And the last one, of course, the last row, you see the first and the second element will multiply with 0, so they will be all gone. The one that survive will be the last in each of the column, you see, the last in each of the column. So you got this, okay, so you got this. And of course, it will be the same as you switch your identity here, okay. You are going to get your A back here, okay. It will be pretty much the same, okay. Another thing that you may need to know is the power of a matrix, okay. So if your A is the square matrix of order n by n, the A raised to the power p, it means that you are going to multiply your A by p factors or p copies. And if you have your A raised to the power 0, you are going to define it to be the identity matrix In. Okay, so for example, if you need to do the A cube, okay, with this matrix A, okay, of course A to the 0, this is a definition, okay, so you define it to be the identity of 2 by 2 matrix. A to the 1, of course, it is the A itself because it has nothing to do, right? But A square, it is your A multiplied by another A. So you are going to do a row multiplied by a column again, right? So this one, it is 1 and negative 1. So together you got 0. The first row, the second column, 1 and 2. So together you got a 3. The second row, the first column, so you have negative 1, negative 2. So you have negative 3 as a result. And the last one, the second row and the second column, so you have negative 1 and 4, which is 3 as a result. So here is your A square. So if you need to find the A cube, then you apply another A to your A square, right? So here your A square, there is your A. So you do one more time, okay, this one multiply. So you are going to have 1 and 0, which is 0. 1 and negative 3, which is negative 3. So this is the result for the first row, first column. The first row and the second column, you got a 3 and a 3. Together it is a 6. The second row and the first column, you got 0 and negative 6. So you have negative 6. And the last one, the second row and the second column, you have negative 3 and 6, which is a 3. So here is your A cube. So I mean, you can figure it out by yourself what is your A raised to the power 4. Okay, so you just multiply A one more time to your A cube. What will be the result? Okay, so we are going to stop the fundamental operation of the matrix and also a fundamental thing about the matrix right here, okay, at this clip, and we are going to make use of the matrix notation and also a multiplication of a matrix to do some further application in terms of system of linear equation on the next clip. Okay, we'll see you then. Bye bye.